One more. So, looking at a problem kind of like we did with the garden, but we've got two wires carrying current at the corners of a square now. One's going out and one's going in. We're going to look at the point O, origin. At the origin, draw and label the field caused by each wire. Use B1 for the current from I1, B2 for I2. Also draw the total field. Okay, so I1 is going in, and so it's going to be thumb down and the finger's going this way, so it's going to be a field perpendicular to the radius. So we're going to have something like this for B1. B2 is out, so it's going to be going around counterclockwise then, and we need a radius, be perpendicular to the radius, and it's not twice as far, but it's twice as big, so it'll probably be a little bit bigger, something like that for B2. These are vectors. And then it says find the total field. Let's see, so we can draw a parallelogram, or however you like to add vectors, something like that. So the total field might be something like this. Add 1 and 2 together to get the total field. All right, determine the total magnetic field at O. So B total is going to be B1 plus B2. And again, they're vectors. We got to add them as vectors with their components, and things probably aren't going to cancel this time. But let's get the magnitude of B1 first. B1, again, they're long wires, so we're going to do mu naught I over 2 pi r. Make these for 1. So we got 4 pi 10 to the negative 7. I1, 1 amp, 2 pi, and R1 is the side of the square, half a meter. All right, so we've got 2 times 10 to the negative 7 divided by 0.5. That's all that ends up being left. Okay. 400 nanoteslas, and let's just go, okay, and then let's go ahead and get the direction. So B1 as a vector then. This one's a nice one since we're straight in the x direction for the radius, then the field itself will be straight in the negative y direction, so it's just going to be negative 400 j hat, negative j hat times our 400 nanoteslas. Good. B2. Magnitude first, mu naught I2 over 2 pi R2, 4 pi 10 to the negative 7, I2 is 2 amps, 2 pi, R2 is hypotenuse of the triangle, square root of 0.5 squared plus 0.5 squared, 0.5 squared times square root of 2, but let's just go ahead and do it. Square root of 0.5 squared plus 0.5 squared, yeah, 0.7071 meters. So 0.7071 meters, plug that in. Let's do some canceling here first. 2e negative 7 times 2 divided by 0.7071. All right, 565, I guess, I don't know, keeping an extra sig fig for some reason. Nanoteslas is magnitude of it. Getting B2 as a vector, so we're going to have that magnitude, 565.7. And then, let's see, we've got our triangle here. It's a square, so we've got 45 degrees here, or 45 degrees. Get a horizontal, oh, let's just do vertical, 45 degrees there. Oh, 45 is making it easy here. Just be careful where when you do these kinds of things, that you get your angles, keep track of your angles correctly. Let's just do it. So if this is 45, this is 90, that makes this one be the other 40. If this were just theta in general, this would also be the theta, which is 45 in our case. So we don't have to be so careful. But on the test, it might not be 45 degrees, so be careful. All right, so in this case, the x component of B2 is the cosine. So cosine 45, and it's positive x, so just the I hat. And the y is positive too. The j hat's positive, but it's sine of the angle, so sine 45. All right, so plug those in, 565.7 times, we'll just do sine of 45, 400. I hat plus 400 j hat nanoteslas. Okay, that was convenient. All right, so that B total probably is going to be just flat, even though I tried to draw a little bit down. But that's okay. If you don't know ahead of time when you're drawing your pictures, so they may be a little bit off. Okay, so B total is negative 400 j hat from B1. So it's B1 plus B2, just like we had up here, plus 400 I hat plus 400 j hat. All of it is nanoteslas. And so the j parts cancel out to our sig figs anyway, which I imagine they do cancel out. And so we just get 400 I hat nanoteslas is B total. Okay, so it should have been straight. Okay, next part here. Given a 1 millicoulomb charge located at 0 with a velocity of 5 times 10 to the 5th meters per second out of the page, so we've got a charge coming out, positive millicoulomb, so it's coming out with positive charge. Draw the force felt by the charge. So we've got QV coming out, cross B, going that way. V is out of the page, B is X direction, so the force is up. So the force is like this. I mean, up on the page, in the plane of the page, like that, in the Y direction. Okay. Just double check. V, cross B. No, hold on. V is out of the page. B is down. F, Alrighty. Try again. V is out of the page. B is pointing. B total, oh yeah, I did it right. B total is, I was doing B1. B total is in the X direction, so yes, the force is straight in the Y direction. Okay, draw the force felt by the charge diagram, determine the magnitude of the force. So the force, QV cross B, QVB sine theta, but V is straight out, B is straight this way. So there's 90 degrees, so this goes to 1. So force is QVB times J hat for the direction. And so we got 1 millicoulomb, velocity 5, 10 to the 5th meters per second. B 400, 10 to the negative 9 Teslas. I'm just taking the magnitude because we've already gotten the direction from there, so we can kind of ignore the I hat for the moment, since we use the picture to get the force, or to get the direction. All right, so 1e negative 3 times 5e 5 times 400e negative 9 200 micronewtons in the J ejection, J hat. All right, and that's the test, sample test.